So at least I don't need to play any music. But I think the topic that I would like to reflect with you tonight also requires a non-negligible amount of human creativity. So I would like to reflect with you about how science, how the scientific pursuit may look like in this new age that is unfolding in front of us, which is the age of artificial intelligence. And typically when we hear this word, we think about these kind of tools like ChatGPT, for example. And I actually asked ChatGPT to write a sonnet in Shakespeare style about science in the age of AI. And also to generate this image. And another AI program recited this one stanza from the poem. Oh. It didn't. But I think, first of all, it is quite amazing. This result is amazing because even a few years ago, we couldn't make our machines make a coherent sentence, let alone an almost perfect English sonnet. And I think what is also amazing is that the task that this AI program learned how to do was to complete words in sentences in a very big corpus of textual data. So it doesn't know what a sonnet is. It doesn't know how to write sonnets. It has never been taught to do that. And this will be an important point. And I think this connects to what Walter was showing in his talk, that their AI could compose music that experts couldn't distinguish from real Beethoven, but it didn't know how Beethoven composed his music, or for that purpose, it couldn't tell you which three notes sound well together. And nowadays, I think we see AI technologies penetrating our lives with, I would say, scaring pace. Like, for example, this biped robot that, or this self-driving car. We see these tools, we see these applications already in our lives, even if a decade ago that was considered a problem out of reach because of its complexity. And this, of course, brings some people to have a rational fear of apocalyptic scenarios, of robots taking over our societies, enslaving humans. I think this is understandable, but probably a little bit out of place. I think it is in general nonsensical to attribute human drives and motivations to machines. But obviously the presence of AI in our lives brings forth and makes urgent very important philosophical questions, typically of ethical nature, like the classical trolley problem, right? If, for example, this self-driving car in this picture is about to collide with the car in front of it, I think the passenger inside the car and we as a human society, we are very keen to know whether the robotic driver will indeed collide and kill the passenger or will steer away and kill a bystander. And I think other, not less important, but maybe a little bit more elusive questions that we should be asking of ontological nature is, for example, does conscious, whatever it means, some self-awareness, is it a byproduct of intelligence, or is it just a feature of human realization of intelligence? And we can conceive of an intelligent machine that is unconscious. So fortunately, we don't need to answer these questions tonight, but I'm sure that scientists and philosophers are going to ponder them in the decades to come. So what makes AI so special? Let me try to give you a few killing features of these technologies. So for that, let's just remember how we write computer programs, how we write software from the times of ENIAC, that first digital computer that filled rooms with vacuum tubes and wires, until modern day computers. So a program is a set of instructions written by a human programmer and executed by a computer. And that set of instructions, they take an input, transform it in some way, and produce an output. So if for some reason we are not satisfied with how the program works, for example, we want to make it faster, we need the strike of a human genius to come up with a new program that does it better, right? And if the task at hand is important and the new program does it much better to enable something new, then certainly our program will enter into the Hall of Fame of the most important algorithms of the century. And it has a very remarkable list of different algorithms. But AI approaches take a very different perspective. So we think of a program as a mathematical function that maps inputs to outputs, and that function has degrees of freedom that can be adjusted. It has some parameters that we can tune. So computer scientists call such functions artificial neural networks, but don't take it too literally. There is very little connection, if at all, between those mathematical creatures and what we have between our ears. And then there is another important, I would say, fact of life that is being exploited, and that fact is that it is much easier to appreciate that something is good than to create that something. So for example, if I listen to a beautiful piece of music, I know that it is beautiful, but I cannot compose it. So what we can do with these two ideas, we can make our computer output some output. For example, if it is a chess player, it can make a move on the board, and then we can quantify how good that output was. And if we know how to do that, then magic will happen. Basically, we can allow the learning algorithm to update the parameters of the program in such a way that next time the output will be better. And if we play this game many, many times, again and again, we can make our computer, starting with making random moves on the chessboard, beat human chess masters or compose Beethoven's music. So how does this help us in the scientific pursuit? So let me start with a little illustration that I'm sure, I hope, truly hope that people here know what it is. So what it is? It's a cell, right? It's a eukaryotic cell, an animal cell. We have many billions of such cells composing our body, performing different functions. And let me tell you right away, this is a lie. So this is probably a better idea of what we have inside the cell. It's a very crowded place. So what you see here are all the biomolecules at the right scale and concentration. And there is one family of molecules that literally build up the edifice of life. These are proteins. So proteins are responsible both for the structure and the function of a cell. And proteins are substances that are made of a long chain of simple substances that are called amino acids. So we have 20 different types of amino acids that build up a protein. And in the cell, they are created by a little molecular assembly machine that is called the ribosome. It reads genetic instructions and concatenates the amino acids into a chain. And then once this chain exits the ribosome, magic happens. By electrostatic forces that make some atoms attract or repel each other, the protein folds into a three-dimensional structure. Okay? So that structure gives its function and its unique structure. And if you ask the physicist how this works, like for example this guy with the cat that is simultaneously dead and alive, the physicist will tell you that all this protein folding, all chemistry in general, is governed by his equation, right? The Schrödinger equation. The problem with the Schrödinger equation, however, is that we know how to solve it for the hydrogen atom. And when we increase the molecule size, the complexity goes up so quickly that even for a modestly sized protein, we wouldn't have sufficient compute power of all supercomputers on our planet combined to calculate the solution of the Schrödinger equation. So in theory, we know the physics of protein folding. In practice, we don't know how to use it, right? So there is a very big scale gap that we need to bridge. And AI technologies allow us to do that. So I don't know how many of you are aware that a few years ago, a literal breakthrough happened in structural biology with the publication of this paper by a group of biologists and computer scientists from DeepMind, a Google company. Basically, what they published was an AI program called AlphaFold that predicts protein structure from the sequence of amino acids. So what they used, they actually took a corpus of data that is called the protein data bank that has experimentally determined protein structures like this hemoglobin protein that transports oxygen in our blood, and the corresponding amino acid sequences, and they learned a map between these sequences to structures. So, of course, once we have this model, we can invert this map and, for example, design proteins that have some specific structures, specific properties. And this is, of course, important in material science, in biotechnology, in medicine. The most remarkable thing, however, is that AlphaFold doesn't know how proteins fold. It doesn't know the physics of protein folding. It never learned it. However, it can make useful predictions. And I think this is something that we now have in the age of AI. We have black box models that explain data, can make useful predictions. What else would you need from a scientific model, or a scientific theory, if you will? So I think there is probably, it's about time to maybe rethink how the scientific method works. And it worked amazingly well so far, since the times of Galileo Galilei and Isaac Newton. How did it work exactly? So a human scientist observed some natural phenomenon, for example, an apple falling from a tree, and then hypothesized some rule, some law of nature that governs that phenomenon, like, for example, this equation for universal gravity. And then from this hypothesis, we can make a prediction. We can hypothesize, for example, we can predict that if this law is correct, the planets in our solar system need to have elliptical orbits with some quantitative characteristics. Then we can take our telescope on a starry night, measure planetary motion, and verify whether this equation is correct or not. And actually, I find this humbling in some way. This is what, according to Frank Wilczek, Nobel Prize laureate in physics, what he calls the core theory. This is all fundamental laws of physics that we know about our universe today. So from the subatomic particles that are governed by quantum field theories up until the biggest structures of the universe that are governed by Einstein's general relativity, all of these laws of nature are captured in this equation. Okay? So, and let me try throwing some maybe heretic thought. Maybe we are done with systems that are effectively described by this language. And especially biological systems, like our brains, for example, maybe they simply don't admit a simple description by that grammar. If, for example, I give you a differential equation with 50,000 terms, will it be useful as a scientific model? Probably not so useful. So the same way we allowed our software not to be human interpretable anymore, we allowed black box parts into our software, maybe we should allow black box scientific models as well, like AlphaFold. Models that can make useful predictions, but we don't know how they do that. And because these models are fed by data, by empirical data that we collect in experiments, maybe we should also rethink how experiments look like. Because nowadays, experiments are designed by human scientists for human scientists. We would like to be able to interpret the data. But if we delegate the interpretation to a machine, maybe the machine should also design the experiment that is in perfect concert with what is going to happen next. Maybe the data we collect will be more efficient and more useful. So I don't know how and where this path is going to lead us. I don't know what the future holds. And I'm still pinching myself to believe that I'm quoting from a machine-generated poem, but I actually like the questions that it is asking. I personally want to hope that even if by delegating some of our scientific work to machines, we will lose a little bit of our hands in dirt, we will still remain as humans valuable and meaningful partners of machines on the path to the pursuit of science. Thank you very much.